Hey everyone, and welcome to This Explainer. Today, we're diving into something absolutely fascinating. We're going to look at how the microscopic science of material fatigue is actually a universal masterclass in risk mitigation and quality control. Whether you're managing a super complex engineering project, overseeing a huge industrial supply chain, or honestly, even if you're just fascinated by how things work, understanding how we uncover unseen flaws in solid metal offers some incredible insights. It literally shows us how to prevent catastrophic failures in pretty much any system.
So you might be wondering, what can an exploding 1950s jetliner teach us about managing today's massive billion-dollar projects? Well, to hook you right away, we have to look back at how a microscopic flaw literally brought down an entire fleet of the world's first commercial jetliners. The principles of how small, unnoticed problems compound over time, yeah, they haven't changed. If anything, they've only become more relevant as our systems get more and more complex. The de Havilland Comet was an absolute engineering marvel of its era. But tragically, it suffered catastrophic mid-air structural failures, and it was all because of an invisible enemy. You see, the Comet was designed to fly higher than ever before, which meant the cabin had to be pressurized so passengers could, breathe. It was essentially a pressurized balloon wrapped in an aluminum skin that was just 0.71 millimeters thick. So why did they suddenly tear apart in the sky? Let's dive into Section 1, the slow-motion disaster. To really understand this unseen threat, we have to unpack why structural failure isn't actually sudden at all. It's a slow-motion disaster. We usually think of breaking metal like, snapping a twig, just a sudden single event. But in complex machinery, the absolutely crucial concept is fatigue life. This tells us exactly how much cyclical stress a piece of metal can take before it just gives up. Every single time the Comet flew, its fuselage was pressurized and then depressurized. The designers knew this, but they assumed that because the plane could withstand 2.5 times the normal pressure in a single, one-off test, this daily cyclical stress wasn't going to be a problem. Well, they were fundamentally wrong. I want you to think of fatigue life as a crack bank account. Every single pressure cycle, every vibration, every takeoff and landing, it all acts like a withdrawal. It takes a tiny bit of life away from the component, and eventually, that balance hits zero. The failure's happening slowly, microscopically, over thousands of cycles, long before anything visibly breaks to the naked eye. When that bank account totally empties out, we reach what's called the critical crack length. This is the terrifying mathematical point, calculated by things like the Paris-Erdogan equation, where the material simply can no longer handle the stress, and the microscopic flaw fractures instantly. Once a crack hits this critical length, it's game over. It propagates at the speed of sound, leading to a massive, explosive rupture. Now, when forensic engineers look at broken pieces under a microscope, they search for what they call beach marks or striations. Just like cutting open a tree to look at its rings, these marks left behind on the metal act as an exact historical record. Each microscopic ring represents the crack growing over time, cycle by cycle, until the ultimate failure. It is the literal fingerprint of a slow-motion disaster. Moving right along to Section 2, the sharp corner problem. Getting into the physics of the design, this is an incredibly vital concept. And honestly, it's why our modern world looks the way it does. Metal literally likes smooth flow lines of stress. Imagine stress flowing through a solid object almost like a river of water. Sharp corners create kinks where that river gets jammed up and stress fatally piles up. But rounded corners, or what engineers call fillets, allow that stress to flow safely and evenly around the obstacle. Engineers use a mathematical value called the stress intensity factor to calculate exactly how severe this stress pileup is near a sharp corner or an existing crack. If you have a sharp notch, the stress concentration factor absolutely skyrockets. The local stress right at that exact tiny point is massively higher than the overall stress on the entire machine. And guys, this was the Comet's tragic flaw. To save on manufacturing time, they used punched rivets instead of drilled ones, which actually left microscopic manufacturing defects in the metal. But even worse, the aircraft featured square-shaped windows. Those square corners acted as massive stress concentrators. They were literally sharp corners in the structural river, piling up stress with every single flight until a crack formed, grew, and violently ripped open the pressurized cabin. Okay, Section 3, Hunting the Invisible. So how in the world do we catch a microscopic stress fracture before the bank account hits zero? I mean, a flaw that is literally invisible to the human eye. We use non-destructive testing, or NDT, and one of the most visually satisfying and effective methods is using a bright red dye penetrant. Mechanics spray it onto the metal, wipe away the excess, and then apply a developer. The red dye literally bleeds out of the microscopic cracks, painting a stark, impossible-to-miss red line right over the invisible danger. We also use other methods, like ultrasonic testing, which sends sound waves deep into the material to map out internal flaws. But sometimes, to truly understand a systemic failure, we have to test things to destruction. To prove exactly why the comet was crashing, investigators built this massive 34-meter-long water tank. They submerged an entire comet fuselage, filled it with water, and continuously flexed the wings with hydraulic jacks to simulate flights. Now, they used water instead of air so that when the plane finally ruptured, it wouldn't explosively destroy all the evidence. After weeks of simulated flying, the systemic flaw revealed itself, tearing a massive 2.4-meter gash right from the corner of a square hatch. As analyst Brady Haywood profoundly noted, the true limitation in these tragic engineering failures is often simply our inability to imagine what could go wrong. The comet designers had all the math in the world, right? But they simply couldn't imagine that a single pressurization cycle per flight could slowly, methodically destroy their plane. This failure forced an entire industry to dramatically expand its imagination regarding risk. Which brings us to Section 4, the economics of grounding. When that unseen microscopic flaw finally becomes visible across a whole fleet, the business reality hits really hard. We see this risk compound even further when we look at the story of Aloha Airlines Flight 243 back in 1988. This aircraft suffered explosive decompression because of widespread fatigue damage. The lap joints at the aircraft had severely degraded due to a highly corrosive island environment and just a rapid accumulation of flight cycles. But crucially, the airline had fragmented their major D-check inspections into 52 separate, smaller work packages. This completely disjointed inspection strategy created massive blind spots, allowing a highly corrosive environment to literally tear the roof off an airplane mid-flight. When systemic issues like this are found today, aviation authorities issue a global mandatory service bulletin. They ground fleets for inspection and repair. Now, make no mistake, grounding a fleet is an economic nuclear option. It costs companies tens or hundreds of millions of dollars. But companies take this massive financial hit because the alternative, the billion-dollar asset loss and the infinite human cost of losing just one more machine, is simply unacceptable. It is the ultimate lesson in proactive risk management. And finally, Section 5, Lessons in Risk Mitigation. Let's pull this all together. How does this extreme aviation science apply to your daily project management and quality control? Well, if a microscopic rivet defect or a sharp window corner can ground an entire fleet of billion-dollar jets, imagine what a tiny, unchecked oversight in a project schedule, a software codebase, or a construction supply chain can do to your bottom line over time. Small, repeated stresses, whether they're mechanical, financial, or organizational, they all withdraw from your project's fatigue life. And if you're doing fragmented inspections, just like Aloha Airlines, you're going to miss the widespread damage until the whole thing fractures completely. So, I'll leave you with this provocative thought to explore further. What are the sharp corners in your organization? Where is the stress piling up because of poor design or rigid workflows? Are you just passively waiting for those pressure points to hit critical length and catastrophically fracture? Or are you actively hunting the invisible? Thank you so much for joining me on this explainer. Keep questioning, keep inspecting, and I'll catch you next time.